there's an ironicness about this. It was about reliability. I hosted a session at Intersolar North America that proved to be standing room only on this subject. Unfortunately, some of the key people that I wanted to actually bring back onto this panel unfortunately weren't even going to be attending this event. So we had to change track. But ironically, my laptop decided to fail with a hard drive failure. So reliability I should have kept with the reliability topic. I may not have had the catastrophic failure of my laptop while I've been away here. So, but the actual topic that we're going to cover is taking advanced technology from the lab to the fab. We're looking at highlighting where we've seen record cell efficiencies touted by many companies, including equipment suppliers. But when you see the reality of what is actually being manufactured in high volume, there's a massive gap between the two. So it's why is that, and what are the challenges that are, what are the issues behind why technology simply isn't getting in at the high rate that it should do. And there's a knock-on effect as well because of the industry's focus on cost reduction without really seeing overcapacity coming down. And of course, related industries like the semiconductor industry have used roadmaps and tried to beat those roadmaps to introduce new technology that fundamentally says when they introduce that new technology, they're eliminating much of the legacy capacity held by other companies, which actually then reduces the overcapacity in the industry. So bringing in advanced technology is actually part of an industry strategy to get out of a period of profitless prosperity and to actually bring that technology in at a faster pace that helps as well in this currently in the situation we're in, where we need to reduce the amount of capacity in the marketplace. So it's not just about the R&D factors, it's actually about how R&D and moving that advanced process technology into volume production as quickly as possible is actually part of the industry's need to address the current industry climate and the challenges. So with that, I know some of our panelists are here. If they wouldn't mind coming up to the front here, and we'll try and introduce people, and we'll be opening this to the floor for comments as well. Florian. Should be another two, but if we don't, that's fine.
You have to push the green button in order to speak, and it's two at once.
Well, we'll carry on because we can do a lot. Hopefully, we were waiting for a couple of other people, but we haven't seen them, so it's quite a trek from some of the other places to get here. So, but we'll start. To my right is a gentleman, Marcus Fisher, works for Q-Cells, been involved in R&D for many years, and I brought him in as a victim, especially to cover areas to do with technology roadmaps. He's well versed in these issues, and we've confronted him on this topic a few times over the last couple of years. Next we have Florian Hapseckel, CEO, but also a well-known R&D specialist. But I thought we'd bring in the thin film element here. It's not just about advanced technologies, not just about crystalline. It's also very relevant to the challenges faced by the thin film community. We were supposed to have another gentleman on thin films, flexible SIGs, and but he's not here. But the challenge there is this is a startup just literally had announced the start of production over the last month. So it was hopefully we were going to get insight into where they've brought obviously technology right from purely the R&D stage and are now moving into production. But we won't be able to cover particularly that side, but I'm sure Florian will help us out in that area as well, having done that with Calypso. On my far right is Nick Sarno. Many people may remember Nick as head of manufacturing at LDK, formerly very well-known polysilicon man and wafer material specialist at MEMC. And again, with the materials aspect crucial, I thought it would be good to bring in someone with his expertise. He's now running his own consultancy firm for many manufacturers around the world. Well, gentlemen, thank you very much for allowing me to drag you out of normal business for this session. I'd love to kick off really with Marcus. We've seen record cell efficiencies being announced over the last several years. In reality, we're seeing maybe a 1%, a 0.5% rather, conversion efficiency migration into volume production. And we've seen this with both thin film and crystalline. It's not just been a crystalline issue. Is there a fundamental problem in that everyone, because there's no cohesive, collective roadmap for technology migration and introduction, is that at the root cause of why we simply can't seem to get technology, in there at say 1% leaps, 1.5% leaps per annum? Is that a core part of the problem?
So first of all, thank you for the invitation. I don't feel like a victim, but I like those events and the possibility to discuss some topics. So I'm as Q-Cells member within this roadmap ITRPV, and so thank you for referring especially these points. And within the ITRPV, we especially in the product area focus on the point efficiencies and module powers there. And we explicitly mean there module powers and cell efficiencies that come out of standard production lines. And at least it should have, or should represent about 10% of the production capacity of a company. This is one point that is very important because of the difference between this world record cells and the current production outputs. So, because having records is one thing, and it's nice to have this certification there at the wall, but nevertheless, bringing this into production, this is a challenge, and transferring from lab to fab has to be well prepared. Otherwise, you have to retransfer it from fab to lab. And this is a disaster for every company if you have to go back to restart again. And new cell concepts are possible for these two approaches. So there are the revolutionary approaches. That means, okay, we start with a completely new concept of technology and introduce this into mass production. This is one way. The other way is the evolutionary concept. So, and what we currently see is there is a mixture of both in the community. So, and the evolutionary step that is currently of much more interest because it can make use of existing tool sets. It may apply upgrades of the retrofits of the machines that are available. And having this approach, you are able of proving the efficiency or the technology concepts before rolling them out into the mass production. This is the best way. Nevertheless, you have also to be fast, and this is always a trade-off. It's always a trade-off. So, and we currently, as Q-Cells, so we are about to transfer one technology into mass production, and to be honest, it took 2 to 3 years to prepare everything. And actually, we are in the rollout phase, and we have still a gap between these record cells. So we have running monitoring processes for our quantum technology. They go within 18 up to 80.8%. In an average, we have 18.2 to 3 in the mass production, and during the ramp-up phase, we are approaching this efficiencies. And within the startup phase, and what is much more important is that you also have this yield issues and this reliability issues under control, and that's why it takes a while. Yeah, it takes a while to implement such a new technology. It's not a contrast, but it's part of the implementation process, and the companies that manage this transition process best from lab to fab, that will make the race. And we have this approach to debug the process before rolling out into mass production. And I think this is a good way to avoid this step back, fab to lab. This would be the worst thing.
Well, you mentioned back from the fab to the lab. We've obviously had in the thin film space, we've had GE. Not the smallest company in the world or lacking resources, simply do that recently. Florian, do you see that as a specific issue just for thin film? Because obviously it's trying to push those the module efficiencies to ultimately just comparably compete with crystalline. And is that a fundamental flaw of risk all and then realise you're not going to achieve those comparisons or comparable performances?
First of all, also, thank you very much for having me here. I think there is a fundamental difference, as you have just said, between a crystalline production process and the thin film process. And the big difference is that you have really the whole value chain in the thin film production process. This means when you're rolling out here a new line and you're not reaching the yields and the efficiencies and the uptime which you have been calculating with, very fast the whole product gets much too expensive. While within the crystalline world, you most often only ramp up a specific part. For example, you're ramping up a new cell line or a new module line or something. Here you have to do all integrated, and that can be very costly. Also, with regard to your question to GE, my expectation is that they have just seen that if they roll their technology out, and if with efficiencies which are not as good as they want to be, they will very fast have a product which is just not feasible in the market, and they will make a lot of losses. If you also look at each of the big thin film companies, whether it's First Solar, whether it's also GE, or even it's our smaller company, you normally have a rule that you have to invest something between 100 to 200 million euros in ramping up and in introduction into the market. And I have not seen a lot of companies who have been able to get into the market without spending this kind of money. And I think here the question is really, when are you ready to put a lot of this money out in order to do the market introduction? And my expectation is that GE decided, look, our technology is not as good with a difficult market environment, that we believe that this is now the right timing for investing that money. We rather have to wait a little bit, hope that we are better in our roadmap, and then we do that step and make money with that. And with regard to that, I think it's a logical decision from GE. I don't know in detail their results and where they are, but I expect that it makes sense in the current environment. We see hardly any company, I think, besides First at the moment, really making money in the space. So on the one side, I think it shows you that that GE might be really on the right process with their technology, because, as I'm saying, only First Solar with the cadmium telluride is really making money. On the other side, you got to be at least as good as First, and if you're not able to do that with the cost roadmap, you know, it's not really worth going into the market.
Well, Florian, you raise a lot of good issues there. I used the example of GE, but we've also now seen the example of TSMC. You know, with their technology partner, yes, they've built the facility, but like many startups in thin film, they're not really going into volume production. You know, they've realised, just like GE, they've got to go back, relook at the the roadmap, not just for efficiencies, but the costs of those efficiencies. You seem to be in a sort of a lucky spot in the sense you went past that pain barrier, but the challenge I want to throw back to you then is, how do you keep competitive? You've obviously got to have a roadmap that is pushing both those efficiency gains, but at a competitive price. What's going on there? Give us a bit of an update, please, on how you think you're managing that.
So I think, you know, we as a Calyxo had a very clear strategy saying, look, we are going to produce more or less exactly the same module as First Solar. We will be a fast follower, and we go into the niche wherever, you know, First is not going to. And that is working quite well up to now, because when they're producing more than 1 gigawatt, it's somehow possible to place your 10, 15, 20 megawatt somewhere, you know, in that area. And we said, look, we are going to do that, and while we do that, we want to prove that our technology is even better. And I think right now we are at a level where we are very close, so our efficiencies are comparable to the ones of First in the mass production. But a good example is that the second line, which we are actually building at this point of time, and we are ramping up these days, and first modules will come out in October, we earlier had decided to go to larger modules, so we wanted to do 1 by 2 meter modules. But we have gone back from that because we said, look, at this point of time, we will not have the resources to introduce a new module. It will cost you a lot of money to do that. Until you have the acceptance, you will have lower yields at the beginning in the line, you will have lower uptime and so on. So we said we cannot do that. We will start with a smaller module, and then if times are better and there's also a much, much higher request from customers for specific solutions instead of only the price, we will be able maybe to introduce this larger module. So that is, I think, the one area you have to decide that you do steps which are not too costly and where you're quite sure that you can reach the goals fast. On the other side, I think there's at least in thin film, a general rule. You know, if you, but it's also in crystalline. If you have a best cell, it's, you know, by a small cell, you normally are able to produce a module, or should be able to produce a module with around 2% less absolute efficiency based on that cell. Now, we, for example, have best cells over 17% in our labs. And now you have to ask your two kind of questions. The one question is, and Marcos already said that, how near is the process from the lab to your production line? Because if this is something totally different, you know, it doesn't help you for your production line right away, but you know, it's nice because you have gained some insight, but it doesn't help you on the daily basis. And there, for example, what we are doing is really we are only working with depositions which we have done originally in our production line. So we don't do any specific deposition away, but we only do that because we say, look, we need to get here our advantages. And then the other question is, you know, why if I mean, for example, for our company, best module is only a little bit over 13%. Why the hell are we not at 15%? What we normally should be able to do based on the quality. I think there it's really, the answer is very clearly that it's a lot of hard work in order to be able to produce then a few hundreds of best cells on one module. And that is just, let's say, daily work. You have to control your line very thoroughly. You have to have very constant production processes. And this you're doing on a daily basis by getting your distribution of the modules very closely together anyhow. So in my opinion, this, the question of bringing a best cell into your production processes has a lot to do how you're running your production on a daily basis. And if you know how you can control that, and if you're really good, you will be able to do the transfer fast. But if you don't have a very steady production, if you don't have all your control measurement of all equipment, a good MES system and so on, you will not be able to transfer that. And for that reason, and that is where I said it at the beginning, that is where all the money goes to in the end. You need to have a very stable production to be able to transfer a technology. So if anybody comes out of university with a good cell, yes, you need the 100 or 200 million until you will be able to produce that into a large factory.
Well, I wanted to bring Nick into this on the from Florian's perspective, where he's saying you've got the technology, but you've also got to be cost conscious. We've seen, obviously, in the polysilicon market and general materials taking, obviously, a huge, price reductions. The margins have shrunk. But they need to introduce, correct me if I'm wrong, new technology that not only, obviously, from a purity point of view, keeps either increases purity, but also enables them to reduce the cost, because they're at a point where they're manufacturing and selling basically at cost level. So is there a challenge there? How do you go about doing that? How do you bring in a new, from the R&D perspective, because you still got to run these plants. If you close those down, you lose out. It's a tough area, and I'm not quite sure who's doing that right at the poly end of this.
Thank you for the invitation, Mark. I appreciate that. Polysilicon, I think, as I walk around the show lately, it's a bit of a dirty word nowadays anyway. I think there's a total underestimation by many of the new players that entered the market as manufacturers of polysilicon. Of course, it was easy to manufacture a few years ago when prices were, when polysilicon was being sold for $100 plus a kilo. And of course, you had an evolution of other types of processes coming online, upgraded metallurgical silicon. But essentially, when you look at the industry today, you really are back to the basic two technologies out there, the Siemens technology, if you will, and then some fluid bed or granular polysilicon, as some like to call it. But that's on the minor side of the granular polysilicon. There's only, from a manufacturing scale, there's only MEMC and REC that have that. The rest of the plants around the world, including the incumbents, of the so-called Siemens technology. And in actual fact, when you look at the differences between the new players and the incumbent polysilicon producers, I don't believe there's huge technology differences between them, but I do believe that there is huge experience level, if you will, between these players, and that's what makes the difference in terms of manufacturing cost in the polysilicon side. And what's happened with the incumbent players, of course, that some of these guys have got 50, 60 years experience and have provided polysilicon to the semiconductor industry. Semiconductor industry has pushed them for all these years to improve not only their quality but also their cost structure. And of course, the new players in the field, and this is not all of them because there's some very good ones out there, the new players in the industry have not had the same impetus and the same push to either improve quality or to improve cost. And so what's happening lately is that we've seen an awful lot of these plants that sort of sprang up a few years back, tremendous investment money went into the industry, are now really shut down. There's only a number of players that are new players anyway that are doing somewhat well, but at these kind of prices level, you're looking at, I hear numbers such as $20 a kilo on the spot market. Don't forget the old days, going back in 2007, 2008, polysilicon went up to $300 a kilo. So what I do see, Mark, is so small technology changes coming in, if you will, but the technology has been around for a long, long time. For example, there's a technology called hydrochlorination, which does away with a certain portion of the polysilicon plant, and so that brings about a small cost reduction, if you will, significant, but it's still small. The major factors in polysilicon still have to do with what I would define as manufacturing excellence, and this is where the incumbent polysilicon players have really developed this know-how and manufacturing excellence over the years. You know, we've reached a point in polysilicon, I think, that small improvements are possible, in particular with some of the newer players, but there's not going to be huge cost-saving activities. Because these plants that came online 3 or 4 years ago, they were rushed into production, if you will.
Okay.
And so a lot of the systems that would, for example, recover heat or recycle a lot of the byproducts that come out of making polysilicon were not really implemented. And so what you're seeing right now is the upgrading of some of the polysilicon plants to these smaller changes, if you will, that will bring about a very small cost improvement. But the majority of the cost, in particular with the new players, is really not given by the technology itself, but really given by the manufacturing, what I define as manufacturing excellence and know-how.
And I'm assuming an element of scale in there, because, you know, the idea that, well, potentially a wishful idea, you know, a positive wishful idea was that we'd get multiple new players into the polysilicon game, which by nature of the competition would drive the costs down. But they were the ones coming in with the new innovation, you know, looking at every, you know, because they could come with a fresh start and bring in new technologies that enabled, you know, less waste, therefore lowered the cost, but also improving with waste you get impurity issues. So bringing it all together, but at a much lower capex rate, because their capacities to be profitable would have been maybe 5,000 metric tons per year.
Right.
But we've just seen, you know, several companies with double that close down because they simply can't do it at that cost.
Yes, it's interesting when you look at the very front end of the industry, again, polysilicon, and we talk about capex, for example. Again, a few years ago, and I'm only talking maybe 3-4 years, if one was to build a polysilicon plant in China, for example, where most of these plants were being built in Asia, but primarily in China, you were still looking at in the range of $80 to $100 a kilo in capex. So as soon as you had a polysilicon plant that was anywhere close to 10,000 tons, you needed $1 billion for a 10,000 ton plant. You know, one of the big changes in the industry, if you will, today is that if you do want to build a polysilicon plant in China, it's only going to cost you around $60 a kilo in capex. But that's come about basically as a consequence of equipment manufacturers that have also sprang up like mushrooms in China. And so there's been tremendous advances in, and again, in the capex. I think Europe and the US has maybe followed suit a little bit, but not as good as what you get in China. But on the OPEX side, or on the cost side, one of the reasons we're seeing a lot of these facilities that have shut down is that they just cannot get their cost below a certain level. And you know, again, for the new players, this level ranges between, in my opinion, between, you know, anywhere from $30 to $45 a kilo. And we know current spot market prices are around $20 a kilo or so. And that's why these guys are all shutting up shop.
You wanted to add in there, Marcus?
I really like this comment, because this was exactly what I, in my plenary session yesterday on the PV SEC, I mentioned this tremendous shift from focus, especially from the polysilicon point of view. In the last years, we had the opportunity to use polysilicon due to low price. Yeah, so currently, or since 2010 to 2012, the price or the cost distribution from for a module from looking on the 4 parts polysilicon and cell conversion and wafering, cell conversion and module were equally shared. Yeah, and there the price for a module was around $1.80. Yeah. So, and currently the price is about 80 cents for a module per watt peak, and the distribution shifted tremendously. So the polysilicon price cost actually it's about 12%, yeah, and then you have also this wafering changed to about 20% of the overall cost, and cell conversion as well. So you have half of the cost is caused by the cell, including silicon and wafering. And now for module, we have about half of the cost of the module is really caused by the module conversion. Yeah, and this tremendous shift focus again now on all material levels. So we have to lower the to further reduce the price, and finally the cost is the base for the price, or should be the price for the price. Currently, it's not quite sure, because some companies have to sell to get at least some cash in. Yeah, and so the material improvements and material consumption reductions, optimizations are in the focus again, and especially on if really this cost structure or the price structure is approaching the cost structure, it's a tremendous situation, and especially in poly. So you neither see a real promising new technologies that could be applied. Yeah. So, and only continuous improvement can be done, and so it's currently very, very difficult to place a new technology from the lab to the fab due to the current cost situation. Yeah.
Yeah, I believe there's still room for new technology to be developed. The problem is that most, and there are a number of technologies out there that have in my view, have a promise in terms of being able to manufacture at a lower cost. The problem is the money's no longer there in the industry. Yeah, a few years ago, if you had any technology, you could go to China and sell it to somebody. There will be somebody buying technology. Personally, I don't believe there's a huge difference between fluid bed reactor polysilicon, again in terms of cost, and the Siemens. There's not a huge difference there, so that's not gonna be the difference. But there are a number of technologies that I personally try to follow, but it's still, in my opinion, a long way away, not only in terms of being fully developed, but also in terms of funding, that can introduce a much lower production cost if you're able to make the step.
I know where you're going with that, but I wanted to bring in as well a piece of technology is wafer-based. It's moving, the issues of moving to an N-type wafer over a P-type. Is that part of that challenge? Is N-type too much? There's too much cost in an N-type. Yet we all know high efficiency cells back contact. I mean, all of the cell concepts are pointing in that direction of N-type, but we're just not seeing enough of it.
Well, this is one of the dilemmas when you look at polysilicon. I mean, theoretically, even a few years ago, certain parts of the upgraded metallurgical silicon. I mean, if you were to pick and choose,
I'm assuming we're talking that's dead now.
It's dead, but I wanted to make a point.
Right.
I wanted to make a point, and the point is that for N-type wafers, you do need a level of polysilicon that is certainly way above what the most, not all, but most of the new players are even able to produce today with Siemens, because they just haven't had the focus and the emphasis on the quality side. So, and that's where the dilemma is, because the push for higher quality or higher grade polysilicon as a consequence of N-type will require that whatever new technology comes out in polysilicon has to have the quality requirements to produce N-type.
I think there's also one other dilemma with regard to, let's say, new technologies getting from the lab into mass production. The thing is that we have seen let's say the standard technology just decreasing in prices quite a lot and cost quite a lot over the last years, which had to do with all the aspects which have been mentioned here, but also just with the constant learning curve which we had there. And so in my opinion, it's just that the crystalline standard technology, it's somewhere still when we're looking at the cost, it's still the base what you have to achieve. And there have been some companies who have been able to really come over that, and I think First was one. At the moment, I think there are discussions how advantaged they are or not. But I think all the new concepts, which theoretically in the Excel sheet, should be extremely good, it's a long way to really prove that. And I think there are, for example, all the CIGS companies, I'm not aware of one of them really at least saying very openly what the cost structure is and showing how it is. And if you question a little behind that, I think it's a lot of discussion. So I think the problem is that it takes, you're in the race against a technology which is out there since 30, 40 years, and it's optimized by hundreds of companies, and then you're coming with a new technology. And I think even that is also true, and Markus will know that even better, within the crystalline field, because if you're if you're putting out a new technology and you're adding 2 or 3 new process steps, in the Excel sheet it works out, but you don't know exactly how it works out in the practice, and then you're starting with that, your actual costs might be even higher, and you have to think about how long you want to play that game, and so I think that's the whole thing. Same with SunPower, for example. Why the hell has not SunPower beaten everybody in the industry? It's the best cell out there, highest efficiency. Yeah, but somehow they haven't been able, even though they're making that now for a long time, to produce it at a cost level which is much lower. So I think that is the major thing, and that is really the question of implementation. And maybe at this point of time and these days, you're best with very incremental steps, because you're sure that you can increase the quality of the cell with that, but you don't have a lot of additional costs. And I think this is what we are seeing at the moment, really more, let's say, incremental steps instead of really changing the world. And once the product is out, maybe the product is nice, but you cannot produce it at low cost level. And maybe even the rest of the industry has done another 20%, 30% cost reduction step, which you have put into your Excel model because you wanted to be very positive in your discussion forums.
One final question on that. We'll open up to a couple of questions. Yeah.
Also, one point. So 4 years ago, we built together our research line, our research center at QCells. So some in 2008, 2009, also other companies did this. So our record cells came out starting in 2010, 2011. Yeah. So it took 2 to 3 years to run these pilot lines in a proper way. And now imagine transferring this in situ and as fast as possible to the floating target running standard processes. So and this is really a challenge. But okay, with the right concepts, you can take this challenge and you can be successful. But nevertheless, there will for the days for the time being will be a gap between this. Will remain a gap between this record cells and between the standard production. And so the record cells that are coming out, they come out now on the out of the pilot lines and of the research lines the companies built up and started as well. So 3 years ago or 4 years ago. So that's a similar way.
Okay. Right. And looking at the time, any questions from the floor? Just wait to the mic, and if you just tell us who you are and who you work for.
My name is Sharif Abdelmasih. I'm with Future Energy Corporation. Thanks for sharing your insights with us. My question to you is more sort of outside, we'll start from outside the lab and then you'll have to go back into the lab to answer it. But basically, from the work I'm dealing with, given where sort of mass scale solar modules are, sort of the efficiency being around sort of 15 to sort of 18%, the majority. If this is sort of where we're continuing with, solar is always going to be sort of a really niche technology when you're talking on the global power generation scale, sort of to compete with fossil fuels and such. You have very low capacity factors compared to that, and so unless you have much higher efficiencies, and that coupled with energy storage, so you can deal with the sort of the peak, sunshine around noon, and then for the rest of the day it's much less. These are sort of, from my perspective, the main two factors. And so it seems like the crystalline technology, the first generation, which is around 15 to 18%, it's taking sort of this incremental approach, which might need to reach the 30% theoretical limit. It's still 30% only, and how long is that going to take? So what's your perspective on sort of the fourth generation kind of technology like triple junction, which I believe right now the two companies that have the record are, if I'm not wrong, one is Solar Junction in California, and the other one is, I believe, Sharp, which are around 53%. And so what's your perspective on these technologies and what the roadmap look like, and how practical you think, and what kind of timeline we're looking at to see them sort of being commercialized?
So then I start answering there. So currently we have in PV a situation that we brought down the cost to a level that I say we compete currently with construction of normal power plants. So this was a situation that is completely different from the situation 2 years or 3 years ago. So we are now in this situation that we have to compete with metallurgical problems, so that means with aluminum production, with steel production, and so like this construction of a normal power plant, of a conventional power plant. So due to the tremendous price reductions in PV modules, and due to this improvement, and also due to this current capacity situation. And first of all, we have now, and this will continue with finding some better ways to really more efficiently use the applied materials, and the materials applied, and the efficiency improvements from the lab will also be introduced. So this is the first step. So and there. The conventional cell concepts have a lot of potential. So there will be modules possible with up to 340 watt peak. Currently, this is the peak watt powers are 270. This are available, and this will go in parallel with continuous price reductions and with improvements. So, and then you really have power generation level prices that are at a competition, so they will come at 5 cents per kilowatt hour. So if you calculate over 25 years, and Then the next step, introducing these next technologies will improve the efficiency and but they are currently very expensive. And if the cost will come down there, so the next step will be interesting. But currently, I think the most urgent problem is storage. Yeah? So that means better integrate this technology into the grids. Yeah? But only putting on all roofs PV that would enable us to really ensure power supply that will substitute a lot of conventional power plants. But you have to find a way to store. And so it's one thing is further improvement of the technology. I think even with 20%, you can live with this 20%. Yeah, and you have so many free space for putting solar power plants, but you have to find political solutions to place these power plants and to distribute then the power. These are the challenges, and we currently with the PV we can pave the way to this really to a really renewable energy society. Yeah? And this is, we are on the right track, and then going beyond this 20%, yes, this would be possible, but it's first is to have really the border bring out the right conditions to efficiently use these current technologies, and there will be even a lot of potential for using this conventional technologies.
I mean, I think I only can agree. I don't think that the capacity factor of the production itself is really the major issue. You can, if you get cheaply a generator with 15% efficiency or 10 or 20, if this is cheap enough, people will buy it and install it. We have enough space. If you walk around here, you can everywhere put up the modules. So I don't think that the capacity factor really is the most important thing. It's about costs, and we've seen that over the last year, and I think a lot of companies have exactly done the biggest mistake by thinking, if I have the highest efficiency, I will have a product to sell. No, it's not like that. You have to sell it at a very low cost. And I think this will continue.
Didn't we see the elimination of premium module pricing?
Yeah.
Based on high efficiency to others.
Yeah.
So
there's no big premium anymore. No. You're totally right. Yeah. If you're too low, it doesn't work because of the BOS costs. Yeah, it doesn't work, and that is, for example, why especially the amorph and micromorph getting into troubles. We also have these challenges sometimes, so you have to work with that. But I don't think that in general this is the major thing. It's really about getting the costs down of the energy which is produced, and this doesn't mean that you need to have the energy produced at a very low area. This is quite independent. I think the more important question is really, as you have said, it's the one thing is the storage, or how you can use the electricity. And I think there it's really one of the major questions is it which power or which parties are getting into this field. At the moment it's a very distributed technology. The large power production companies are not in favor of this technology for several reasons. And only I think if the political directions are made in a way that this is also getting more interesting for them, then you will see a very, very high speed of implementation. But I do not agree that I think the costs itself are in general too high, and you see a lot of, or you see projects now starting to be announced and to run totally independent of any subsidies. I think the answer why this is not happening faster is differentfold. The one answer to that is you don't have any necessity to do that fast. With the feed-in tariffs, with all the tariffs, it was always nice because you had to do it until the end of the month, until the end of the year. There was always a pressure for consumers to do the implementation fast because maybe they miss a time of opportunity. If you're working without any subsidies, if you do this year or next year, it doesn't really matter because it's not changing. The only thing which is changing is the prices. So if you're installing a 250 megawatt plant somewhere in Spain, independent of any subsidies, you know, you don't have the pressure of doing that fast. You can do that in 2 or 3 years. You still have the same business case, might be even a little bigger. And I think in this period we are at the moment, we are running out of the subsidies. We have a competitive product, but there are difficulties overall with financing. That is a major thing. How do you finance the thing? And then we have no pressure on doing the things fast. And this is why we're at the moment in this little vacuum. New markets are coming, and that is good. Also new feed-in tariffs. But in order to really have now the big growth, we need to do another step, and we need to help a little bit more with these things I've just said. And I think then you will see a very big market again. Okay.
Guys, we're running out of time. Marcus, Florian, Nick, thanks very much. And give a round of applause, please.
Thanks a lot.